Alright, let's finish up this problem. So we're looking for the frequency. I'm actually going to also look for the wavelength once we solve this. So we're almost done. So h times f, Planck's constant times the frequency, is 12.75 electron volts, and we need to convert that to joules, right? So we learned that 1 electron volt is 1.6 times 10 to the minus 19th joules. So 19. And when we do that in our calculator, let's see, what do I come up with? I get 2.04 times 10 to the minus 18th. 2.04 times 10 to the minus 18th joules. And if we want to solve for the frequency, that's pretty simple. All we have to do is divide both sides by Planck's constant. So we rewrite the 2.04 times, that's a 4, 10 to the minus 18th joules. And Planck's constant is a constant of the universe. It's always the same number, 6.63 times 10 to the minus 34th. And that's in units, let's make sure that looks like a 4. Joules times seconds. Notice the joules cancel, and you get 1 over seconds, which we remember from chapter 7 is, of course, hertz. All right, and so the answer that I get is 3.077, something like that. It depends on where you round. 3.077. So 3 times 10 to the 15th. And remember, it's 1 over seconds, so we call that hertz. So that's the frequency. Now, if I asked you if this was part of the visible spectrum, right? The 3.077 times 10 to the 15th, you could look that up, or you could remember that the visible spectrum is from blue light, which is, I'm not going to do it in nanometers. I did it in nanometers before, 400 nanometers to 700 nanometers, but we'll just do it in meters. So the visible spectrum is from 4 times 10 to the minus 7th. You'll understand why I'm doing it this way in just a moment. Meters. So this is visible. So, to 7 times 10 to the minus 7th. That's not minus. 10 to the minus 7th meters. So from this range is the visible spectrum. So to figure out whether this frequency is part of that, we have to figure out the wavelength. And so from chapter 7, remember, the wavelength of light is the speed of light divided by the frequency. And so see, now that what Bohr's model does is it gives us the frequency, and often we're actually interested in the wavelength. And so when you do this is of course 3 times 10 to the 8th meters per second. This is 8th meters per second divided by what's the number that we just had? Oh, 3.077 times 10 to the minus, I'm sorry, positive 10 to the positive 15th, and that's hertz. And the 1 over seconds up here and the hertz cancel, giving us an answer in meters, and that is 9.75 times 10 to the minus 8th meters. And the question is this a visible photon? Could you see this with the naked eye? And you can only see photons of wavelengths between, this is blue light, and this one, it's 7 times 10 to the minus 7th is red light, and so this is too small, right? This is beyond blue light beyond is probably in the ultraviolet. If I had to guess, this is probably ultraviolet light. So you can't actually see that, but see, the thing is, Bohr's model of the hydrogen atom predicts that, right? Using this model, it predicts, hey, when the electron jumps from the n equals 4 to the n equals 1, it's going to produce a ultraviolet photon, and of exactly this wavelength. And you know, that's exactly what it does. We go and we measure that, and it creates this photon. So that was a good example of Bohr's model. This is showing you the different. So if you did, for example, the n equals 6 to the n equals 2, you would get this frequency. If you went from the n equals 5 to the n equals 2, you would get 6.9 times 10 to the 14th hertz. Okay, and all these, this is what's special about the Balmer series, is these are part of the visible spectrum. You could convert each of these from frequency to wavelength, and you'd find that they're between 4 times 10 to the minus 7th meters and blue light, and all the way to 7 times 10 to the minus 7th meters, which is red light, or the deepest red that the human eye can see. All right, so here's the thing. So this was around 1913, and here's the problem with the Bohr model. It worked spectacularly, explaining the spectrum of hydrogen, but that's it. That's all it did. That's it. That's the only thing it can do. It does it really well. It predicts wavelengths that are outside of the visible spectrum and everything, and we measured those, but that's it. And wouldn't it be nice to have a theory that explains the entire periodic table, not just one element? Although it's the most abundant element in the universe, we'd still want to be able to explain all the other. And so getting back to this idea of, remember in chapter 7 we found that light, photons of light, or light in general, acts as a wave and a particle at the same time. In 1923, this guy named Louis de Broglie made a prediction about matter. He said that, well, if it's true for photons, maybe there is a wavelength of matter itself. And he came up with this formula, and he said the de Broglie wavelength, that's, in this case, that's what lambda is, the wavelength of actual particles, actual matter, like electrons or neutrons or protons, is equal to Planck's constant divided by the momentum. And the momentum is the mass in kilograms times the velocity in meters per second. Lambda will be in meters. Okay, so de Broglie was actually a graduate student in Paris, and he made this prediction. He used some formulas that were around already, one of Einstein's formulas, Planck's formula for light, and he basically put these things together to come up with this formula. This you could actually do with just high school algebra, actually given several equations and coming up with this formula. And so a lot of people wondered, well, what is it? Why did de Broglie win a Nobel Prize for doing something, using some, algebra tricks to come up with this formula? Let me explain that, actually. We'll explain that right now, and then we'll actually go ahead and do some examples with this formula. This is what de Broglie wins the Nobel Prize for. The fact that he comes up with this formula, that's wonderful, but the explanation of why there are certain orbitals and not others for electrons. Basically what de Broglie says is, look, the electron, very much like the photon, is both a wave and a particle at the same time. And if it's a wave, the wave has to be able to complete itself as it waves around the nucleus. And in patterns where the wave is not able to complete, and by the way, when a wave completes itself, these are called standing waves. Any physicist at the time would have known instantly what he was talking about. But when waves do not complete themselves in patterns where the wave does not, end basically where it started, those are not allowed. Those waves are not allowed. Now remember, you go back to Bohr a decade before. Bohr didn't explain this. He just said there are certain allowed orbits, or now, of course, we're going to start calling them orbitals. And de Broglie's matter wave explains that. He said, well, electrons only exist in standing wave patterns, and that was a big deal. That was a pretty big deal. All right, so let's do some examples. So here's de Broglie's formula that he had come up with. Remember, in this case, lambda is the wavelength of matter. It's also known as the de Broglie wavelength, and this is measured in meters. Planck's constant is what it always is, so I'll put that 6.63 times 10 to the minus 34th joules times seconds, and the mass has to be in kilograms for this formula to work, and the velocity has to be in meters per second. Alright, so let's do a quick example. So I'll use an electron, and we know the mass of an electron, remember, from Thomson's experiment, J.J. Thomson's experiment, as well as Millikan's, and that mass turned out to be 9.11 times 10 to the minus 31st kilograms. Alright, so we're going to use that. That's kilograms. We're going to use that. Let's suppose that the velocity of an electron were, I don't know, how about 3.7 times 10 to the 4th meters per second. So that's pretty fast. It's 3,700 meters per second. What's the de Broglie wavelength? Alright, so here we go. So you just put the numbers in, right? So it's 6.67. Sorry, 6.63. Wrong constant. 6.63 times 10 to the minus 34th joules times seconds divided by our mass, which is 9.11 times 10 to the minus 31st. And that's kilograms, and we multiply that times the velocity that I made up, so it's 3.7 times 10 to the 4th. Remember, that's all in the denominator, and it's, of course, meters per second. So all these units cancel except for meters. This is kilograms. All right, so there'll be meters in the numerator when we do the final calculation. It turns out it's probably easier to multiply these two numbers together first, and then take Planck's constant divided by that. Alright, so I'm going to do this in my calculator. Alright, so we put this in our calculator, and here's the answer that I come up with. I get 1.97, I'm going to round it right there, times 10 to the minus 8th. Meters. Okay, so that's the de Broglie wavelength. There's the example. Let me just say a couple of things about this real quick. If you've ever heard of electron microscopes, it's using electrons instead of light as a wave to image something smaller than the human eye can see. For example, this would be a good example. If we took electrons and you're getting down well below violet light, the most blue light that you could possibly see, and yeah, so we do this all the time.